What if the most dangerous part of a suspension bridge isn't what you see? Because inside the main cables, which look like solid metal, there's a structure made of tens of thousands of wires, each one vulnerable to destruction by even a drop of salty fog. So why doesn't a bridge weighing thousands of tons collapse every single day? And what happens if moisture gets inside the cable where nobody can see it? The Golden Gate Bridge in San Francisco has two main cables, each about 37 inches in diameter. Inside each one, 27,572 individual wires. If you unwound all these wires and connected them into one line, you'd get roughly 80,000 miles of steel. That's about 3 times the length of Earth's equator. The weight of just one of these cables? Around 24,500 tons. That's comparable to the mass of a small cruise ship. Japan's Akashi Kaikyo Bridge, one of the longest suspension bridges in the world, has main cables made of many thousands of high-strength steel wires. Their combined length exceeds several tens of thousands of kilometers. Stay till the end. You'll learn a secret that even bridge engineers don't talk about. Picture the classic example, San Francisco's Golden Gate Bridge. It's got two main cables draped over towers and anchored into massive concrete blocks in the rock. Each cable's about 37 inches across. That's not a cable anymore. It's practically a pillar you'd need 2 or 3 people to wrap their arms around. Inside, 27,572 individual wires, compressed into a perfectly round bundle. Unwind all those wires and link them end to end, and you've got roughly 80,000 miles of steel. That's about 3 times the length of Earth's equator. One cable weighs around 24,500 tons, comparable to a small cruise ship or several hundred fully loaded semis. Why so many wires instead of one giant solid rod? Steel handles tension beautifully, but it doesn't tolerate flaws well, especially in large cross-sections. When a cable is made up of thousands of individual wires, each one can give a little, taking on a bigger share of the load in some spots, a smaller share in others. If one wire happens to corrode or weaken for some reason, its contribution to the overall strength is minimal, and you won't even notice it in how the whole cable behaves. Plus, it's way easier to create a flexible shape out of tens of thousands of thin elements. A cable can smoothly wrap around towers, forming a big parabola across the span, whereas a solid rod of that diameter just can't be bent without permanent deformation. The process of making the main cables for a suspension bridge is nothing like how regular steel cables are made at a factory. Nobody ships a pre-made coil a yard thick and thousands of feet long to the construction site. A monster like that would be impossible to deliver or lift into position. So the main cables of suspension bridges are spun on site. It starts with installing temporary working cables between the towers. They run a traveling cart along them that can zip back and forth across the entire span. The cart carries a coil of steel wire. Each trip of the cart means threading another wire between the shores. One end of the wire gets fixed to an anchor on one side. The cart hauls the coil across the span. The wire gets secured on the other shore, and the excess gets cut off. Then the next wire, and so on, tens of thousands of times. To keep this insane marathon from turning into chaos, the wires get organized into what are called strands or subcables. For example, several hundred parallel wires get bundled into one strand of a specific diameter. First, all the wires get tensioned with a little slack. Then special jacks even out the tension, so each little wire carries roughly the same load. Then the bundle gets clamped with rings or special bands to keep it from spreading apart. When there are enough of these bundles, they get brought together and compressed again into a single cylindrical structure. spiral wrapping of thin round wire goes on top to hold the shape, plus a protective layer of paint or other anti-corrosion coating. At this stage, the cable can already hold incredible force. Picture a bridge deck suspended from it, a steel truss or box girder carrying the road surface. This deck structure transfers the load to the main cables through suspenders. Any vehicle crossing the bridge adds several tons to the system, sometimes dozens if we're talking about a semi or multiple trucks together. Wind pushes against the side of the structure with a force that can reach thousands of kilonewtons during a storm. Ultimately, the main cables feel all of this, stretching literally just a few inches along their entire length while staying within the elastic range. The beauty of a suspension bridge is that the cable works purely in tension, not bending or compression. That's the ideal mode for high-strength steel. The modulus of elasticity and tensile strength of these cables are specifically chosen so that working stresses stay well below ultimate limits, even accounting for wind gusts, temperature swings, and heavy traffic flow. During the design phase, engineers model every possible loading scenario. Both lanes completely filled with trucks, sudden braking, seismic events. The result? An acceptable range of cable elongation and sag within which the bridge remains safe and comfortable for users. Here's the fascinating part. Despite all that rigidity, the main cables aren't absolutely static. They breathe with the bridge. On a hot sunny day, the steel expands and the cable sags slightly. At night, as temperatures drop, tension increases and sag decreases. In windy weather, you might notice a gentle oscillation in the deck. The cables themselves are actually moving too, though it's invisible to the naked eye. It's precisely this living, flexible behavior that allows suspension bridges to handle dynamic loads better than rigid, overly stone-like structures. Excessive rigidity is exactly what led to disasters in bridge building history, while controlled flexibility allows the dissipation of vibrational energy. A separate critical topic: protecting cables from corrosion. Steel fears moisture and salty fog, especially in coastal regions like San Francisco. If water and aggressive contaminants get inside a cable, reaching each of the tens of thousands of individual wires, corrosion can silently eat away the cross-section for years until it's too late. That's why immediately after strand spinning and compacting are finished, cables get sealed. First thoroughly painted, then the coating is periodically refreshed. Modern bridges employ additional systems: wrapping with airtight tapes, filling gaps with dehumidified air or nitrogen, monitoring humidity inside. Regular inspections are conducted, including magnetic or ultrasonic non-destructive testing methods, which allow engineers to understand the condition of the wires without opening up the cable. All of this is done so that a single strand of infrastructure can safely serve for decades. The cables of the Golden Gate were designed for a service life of tens of years, but thanks to proper maintenance, regular repainting, and monitoring, they still do their job today, holding up the main span of over 4,000 feet. If you add in other suspension bridges around the world, the picture becomes even more impressive. Hundreds of thousands of miles of steel wire stretched across rivers, bays, and straits, keeping millions of cars suspended in the air every single day. Using main cables made from thousands of steel wires is standard practice for large suspension bridges, so the Golden Gate isn't alone here. One of its most famous relatives is the George Washington Bridge across the Hudson in New York. It also has two main cables woven from tens of thousands of steel wires. The total length of all that wire is measured in thousands of miles, and the mass of each cable runs into tens of thousands of tons, just like the Golden Gate. The same technology was used on the Brooklyn Bridge, though it's older and combines a suspension system with cable stays. There, the main cables also consist of a large number of thin wires spun on-site rather than brought in as pre-made rope. Modern giants are built using the same principle. For example, Japan's Akashi Kaikyo Bridge, one of the longest suspension bridges in the world, has main cables made from many thousands of high-strength steel wires. Their combined length exceeds several tens of thousands of miles, and the design tension reaches hundreds of thousands of tons. A similar approach is used on numerous bridges in China and South Korea, which have been actively building long-span crossings over bays and wide rivers in recent decades. All these bridges share one technology. The main cables are spun on-site from tens of thousands of individual wires, each one tensioned, aligned, and compressed into a unified structure. This technology creates cables of incredible strength and flexibility, capable of holding thousands of tons and handling dynamic loads from wind, traffic, and temperature changes. And so, traveling from a coil of steel wire through tens of thousands of trolley trips across the void, through hydraulic jack tensioning and compression into bundles, through wrapping with protective wire and coating with anti-corrosion paint, the main cable of a suspension bridge is born, a structure of 27,572 individual wires, weighing 24,500 tons, able to stretch several inches under load but staying within elastic deformation, holding in the air a bridge over 4,000 feet long, carrying millions of vehicles every single day. Each wire is a separate element, and if one weakens, it's barely noticeable to the whole system. But if moisture and salt get inside, corrosion can silently destroy wires for years. That's exactly why modern bridges are equipped with humidity monitoring systems, regular inspections, and non-destructive testing. So these giants of steel and concrete can safely serve humanity for centuries.
But an 80,000-ton press isn't just about aviation and space, it's about energy. Massive shafts for hydro turbines, rotors for nuclear reactors, high-pressure housings, all of this demands single-piece forgings of monstrous proportions. Picture a hydro turbine shaft 50 feet long and over 6 feet in diameter. Its weight, more than 100 tons. You can only forge a component like that on a super powerful press. The blank gets heated in a furnace the size of a house, then a crane transfers it onto the press platen, and in just a few strikes, it's shaped into form. Each strike, 80,000 tons of force molding the metal, densifying its structure, squeezing out internal defects. After forging, the part cools slowly, then undergoes heat treatment and machining, but the foundation of its strength, that's laid right there on the press. $80,000 tons. Picture a force that could crush 10 tanks at once. A machine tall as a 10-story building that transforms a red-hot steel mass weighing hundreds of tons into a flat panel like it's Play-Doh. This isn't science fiction. It's the world's most powerful forging press, operating in China since 2013. 80,000 tons of pressure. That's more than the weight of 50,000 cars crashing down on a piece of metal the size of a table. Why did humanity need such monstrous machines? What secrets hide in their history from the Cold War? How did the USSR create a 75,000-ton monster and the US answer with a 50,000-ton press? You'll discover how these metallurgical giants were born, how this inhuman force works, and what can be done under such pressure. Watch till the end. The finale reveals the scale of what humanity creates. The story of giant forging presses didn't start with peaceful purposes. It started with the Cold War arms race. In the late 40s and early 50s, aviation and rocketry demanded fundamentally new solutions. Aircraft were getting bigger, faster, flying higher. Rockets grew in size. And all of this required enormous single-piece components made from high-strength alloys: titanium wing spars, aluminum fuselage panels, steel rocket engine parts. Welding these components together from multiple pieces weakened the structure. Welded seams were vulnerable under load and vibration. What was needed was a technology capable of forging a giant part as a single piece, no seams. That's how the idea of ultra-powerful hydraulic presses was born. The United States understood this first and built several presses in the 50s, capable of exerting up to 50,000 tons of force. The Soviet Union wasn't about to be left behind. At the height of the space race and the arms race, the USSR built a 75,000-ton forging press, an absolute record at the time. The giant machine stood in the factory floor like a metal cathedral, dozens of meters tall, hundreds of tons of structure, hydraulic cylinders as thick as a human body. This press allowed the Soviet Union to stamp out parts for rockets, submarines, and aircraft on a scale that was previously impossible. A solid titanium component several meters long, no longer a dream, but reality. 75,000 tons of force meant that metal of any hardness became pliable material. The Cold War fueled technological progress, and these forging giants were one of its symbols. For decades, these presses remained the pinnacle of engineering. But in 2013, China shattered all records. At one of their metallurgical plants, they fired up a hydraulic press with a force of 80,000 tons. 80,000 tons? That's a force that's hard to wrap your head around. It's the weight of a major ocean liner crashing down on an area the size of a dining table, or pressure equivalent to 50,000 cars stacked on top of each other. The scale of this press is mind-blowing, as tall as a 10-story apartment building, weighing thousands of tons of steel and cast iron, with massive hydraulic systems capable of generating this monstrous force. This press didn't just break a record, it opened up a whole new era of possibilities. Now you can stamp out parts of sizes that used to be considered impossible. Panels for jumbo jets, components for space rockets, reactor equipment, all of this became achievable thanks to this machine. How does a giant like this work? The foundation is hydraulics. Picture massive cylinders filled with oil under monstrous pressure. When pressurized oil flows into the cylinder, the piston starts to move. But this isn't your ordinary piston. Its diameter measures in yards, and its stroke spans dozens of yards. Slowly, but with unimaginable force, the piston descends to where a glowing metal workpiece sits on a massive plate. The workpiece weighs hundreds of tons, a huge ingot of steel, titanium, or aluminum, heated to around 2200 degrees. The metal glows bright orange, radiating unbearable heat. The shop floor fills with the roar of hydraulics, the smell of hot metal and oil. And then, the upper plate of the press begins its descent. Slowly, almost ceremonially. But behind that calm lies 80,000 tons of force. Contact. The upper plate of the press touches the red-hot blank, and the miracle of deformation begins. Metal that's hard as rock at room temperature starts flowing like thick paste under this kind of pressure. 80,000 tons don't give the metal a choice. The blank flattens, spreads outward, takes the shape of the die. A thick ingot becomes a flat panel or a complex three-dimensional part. The process is accompanied by deafening thunder. The metal cracks, groans, excess material squeezes out, flowing to the sides in glowing streams. Temperature, pressure, force, all controlled by computers with millimeter precision. The slightest mistake and a multi-ton blank is ruined, or worse, the press itself can fail. But the operators know their craft. One stamping cycle takes minutes, but the result is a seamless part with perfect internal structure.
Why does this matter so much? Because a single forged part is stronger than any welded structure. A weld seam is always a weak point. Under load, vibration, cyclic stress, that's where cracks start. In aviation or spaceflight, a crack means catastrophe. That's why major structural elements, aircraft wing spars, fuselage panels, landing gear components, rocket engine parts, must be one piece. A super heavy press can forge a titanium beam 30 feet long with no joints whatsoever, or an aluminum panel the size of half a Boeing wing, or a steel blank for reactor equipment weighing 400,000 pounds. Parts like these used to be welded together from dozens of pieces. Now they're made in one press stroke. It's a revolution in manufacturing.
China didn't build this press by accident. The country is aggressively developing its aviation industry, space program, and nuclear power. All of this demands technologies that were previously only available to the US and Russia. An 80,000-ton press is a declaration of technological leadership. Now China can manufacture components it used to have to buy from abroad or settle for smaller dimensions. This is strategic independence. When you've got a press like this, you can build your own aircraft, your own rockets, your own reactors without relying on someone else's technology. It's no coincidence that information about the exact specs and capabilities of this press is tightly controlled. This isn't just manufacturing equipment, it's an element of national security and technological sovereignty. There are only a handful of these presses in the world. Russia has kept its Soviet-era 75,000-ton giants, still running in defense plants today. The US operates its 50,000-ton machines, built back in the 50s and 60s. China now leads with 80,000 tons. There are projects for even more powerful presses, 100,000 tons and beyond. But each of these machines represents a colossal investment. Building a super heavy press costs hundreds of millions of dollars. You need a special foundation that goes dozens of feet into the ground. You need massive hydraulic systems, furnaces to heat the billets, cranes with lifting capacities in the hundreds of tons. It's an entire complex covering the area of a football field. But the payoff is worth it, the ability to manufacture parts that nobody else can. And just like that, through the Cold War, through the technology race between superpowers, through decades of engineering development, humanity arrived at the 80,000-ton press. This isn't just a machine, It's a symbol that we've learned to dominate matter with a force comparable to geological processes. When 80,000 tons come crashing down on white-hot metal, it's like watching the Earth's crust crumple into mountains under tectonic plates. Except here, this process is controlled by humans. Every part that comes out of a press like this carries the imprint of unimaginable force and precision. Planes fly, rockets shoot into space, reactors generate power, and behind all of it stand these giant presses, crushing metal like Play-Doh. This is the story of how humanity learned to create the force of gods and use it to conquer the sky, space, and the atom.
What if I told you the world's toughest roads and roofs aren't born on the construction site, but deep inside oil's blazing heart? A material that survives 360-degree heat and brutal cold. One mistake by the technologist, it turns to stone. But why did this black, sticky residue at the bottom of the oil column become the backbone of bridges, airfields, and massive warehouses? And what chemical secret lets it survive for decades without cracking under 40-ton trucks? Every year, the world produces hundreds of millions of tons of bitumen. It's extracted at temperatures between 930 and 1200 degrees Fahrenheit, squeezing literally the last drops from crude oil. Roofing felt? It passes through vats of molten bitumen at 570 degrees, where every inch of cardboard or fiberglass gets soaked in black gold. One wrong step in the process, and within a couple winters, that road's covered in ruts and potholes. Stick around till the end. You'll discover what even some manufacturers won't tell you.
Picture a massive oil refinery. Giant distillation towers, tall as a 20-story building. Crude oil flows in and gets heated to 650 to 750 degrees Fahrenheit. Fractional distillation begins. Light fractions, gasoline, kerosene, vaporize and rise upward. Middle fractions, diesel, fuel oil, remain in the center. And at the bottom of the tower, a heavy tail accumulates, thick, dark residue. This isn't bitumen yet, but it's already the base for it. This residue goes to a vacuum column. There, it's heated again, but under vacuum, at reduced pressure. This allows even more fractions to evaporate, which become lubricating oils and paraffins, without pushing the temperature high enough to break down the heavy molecules. What remains after this squeezing out of the heaviest parts, that's the foundation for bitumen and tars. But it's still a raw product. Next, chemistry kicks in. Into enormous reactors, they load this residue and add other components. For example, light oils, polymers, modifiers, sometimes sulfur.
At temperatures between 500 and 650 degrees, the mixture is held so large organic molecules partially cross-link, becoming more viscous and heat-resistant. Complex chemical reactions occur: oxidation, polymerization, condensation. Hydrocarbon molecules unite into even larger and heavier structures. The result is a thick, extremely sticky material that becomes solid or glass-like when cooled. It can be crushed into chunks, dissolved in organic solvents, or heated to a liquid state and applied as a waterproofing layer. Bitumen is a close cousin of tar, but with a clear focus on road construction and roofing. It's also derived from heavy petroleum residues after vacuum distillation. In large bitumen plants, it's less about pure chemistry and more about fine-tuning viscosity and temperature behavior. If the bitumen is too hard, it'll crack in winter. If it's too soft, it'll run in the heat at 200 degrees on the asphalt.
That's why the technology has a concept called penetration, how deep a needle enters a sample at a given temperature and load. Engineers tweak the ratio of light and heavy fractions, add polymer modifiers to get a material that won't flow in the heat and won't turn brittle in the cold. In massive mixers, bitumen is heated to temperatures from 450 to 650 degrees Fahrenheit, and under intense mixing, they add modifiers, mineral powder, sometimes acidic or alkaline additives to stabilize the structure. That's how polymer-modified bitumens are born, for high-performance roads, airfields, bridge expansion joints. When people say asphalt road, they actually mean a mix of mineral materials, crushed stone, sand, mineral powder, with bitumen as the binder. In huge asphalt mixers, the crushed stone is pre-dried and heated to temperatures close to 570 degrees Fahrenheit to ensure there's no moisture. Then hot bitumen gets added and mixed until every single pebble is coated in a thin film of binder. The hot mix heads into dump trucks, then straight to the job site for paving. Get the bitumen wrong? A few seasons later, you're looking at ruts, cracks, and potholes. Nail the process? That pavement will handle years of trucks weighing dozens of tons. Roofing felt. It's the story of turning a simple roll of backing into a durable shield against rain, UV rays, and temperature swings. The base is cardboard, fiberglass cloth, or a polyester mesh in roll form, roughly 3 feet wide. Cardboard backing gets picked for budget materials and light-duty jobs, fiberglass when you need better heat resistance and less warping, and polyester for flexible roofs where stretch and tear resistance matter. All these backings share one trait: they're porous, so without treatment they soak up water easily and fall apart fast. To turn a bare base into waterproofing material, the roll gets run through a processing line with vats of hot bitumen or bitumen resin compounds. The liquid bitumen is heated to a range of 450 to 570 degrees Fahrenheit, sometimes higher, to lower viscosity and ensure quality penetration into the fibers. The roll is fed on rollers into the vat so that it's completely submerged in the melt and passes through at a controlled speed. During this time, bitumen fills the pores of the cardboard or fabric, displaces air and moisture, forming something like a skeleton flooded with waterproof mass. After exiting the vat, excess material is removed by calibrating rollers. This helps maintain the specified thickness and avoid drips. Next comes the stage of forming the coating layers. The saturated base passes under bitumen or resin applicators that apply the main layer on the bottom and top. For this, knife or roller coaters are used. A thin gap between the roller and support measures out the coating thickness. The bottom layer handles adhesion to the roof deck or foundation, so it can contain more elastic plasticizers, polymers, oils, special additives that reduce the risk of cracking during bending and temperature swings. The top layer acts as armor against sun, rain, hail, and physical damage, so it's made harder and more heat resistant, sometimes modified with polymers for better UV resistance. While the top layer is still hot and sticky, it gets coated with mineral granules. A dispenser on the line drops a steady stream of mica, basalt granules, or slate onto the moving belt. The particles instantly press into the soft bitumen and lock in place as it cools. This coating isn't just for nice rough texture, it works as a shield against ultraviolet radiation. The sun heats the exposed bitumen surface less, the material ages slower and doesn't crack as fast. Plus, the granules boost abrasion resistance.
After the granules are applied, the sheet moves through a cooling zone. This uses either air cooling or systems with water baths and chilled rollers that pull heat away from the hot bitumen. It's crucial that the temperature drops to a safe level before winding into rolls. If you roll up hot material, the layers stick together, the geometry gets thrown off, and the granules can lose adhesion. To monitor parameters on the line, they install temperature sensors and thickness gauges that ensure the coating layer doesn't come out too thin or too thick. A thin layer means future leaks. Too thick means wasted bitumen and problems during rolling and installation. The next stage is cutting and winding. The roofing felt sheet is cut lengthwise or crosswise into standard rolls, most often between 30 and 50 feet long. Each roll is tightly wound onto a core, so the edges don't shift and the upper layers don't slip. Sometimes one side is left with a strip without granules, covered with pure bitumen.
When laying, this strip gets overlapped by the adjacent sheet, forming a watertight seam that film or granules won't stop you from heating with a torch. Polyethylene or paper liners get added to the roll so the layers don't stick together during shipping and storage. The finished material gets labeled. The tag shows the type of base, the weight of bitumen per square yard, the type of surfacing, the flexibility temperature, and other specs that matter to designers and installers. The story doesn't end there though, because how roofing felt behaves on a roof depends heavily on what exactly got mixed into it back at the factory. If you take regular oxidized bitumen, the material will be cheap but sensitive to temperature swings. On a sunny roof, where the surface easily heats up to 360 degrees in summer, that layer gradually loses elasticity, becomes hard and brittle. To prevent that, polymers get added to the binder. Polymer modifiers make the material more flexible in cold weather and better at handling high heat. Roll roofing can easily withstand both winter freezes and summer scorching without developing a spiderweb of cracks. It's polymer modifiers that gave Rufu Felt new life in the competition with membrane roofing systems. Picture a warehouse complex roof spanning several 100,000 square feet. The classic setup: leveled substrate, a layer of primer from bitumen emulsion, then several layers of roll material with a 4-inch overlap. The bottom layer is often torch applied. You flip it granule side up, heat it with a gas torch until the bitumen softens, and roll it onto the substrate. The top layer goes down the same way, forming a continuous blanket, where the seams are the most critical zones. The quality of that seam determines whether the roof leaks or not. And so, traveling from the bottom of an oil column, through vacuum distillation, through heating to 1200 degrees and oxidation, through vats of molten bitumen at 570 degrees, through coating with mineral granules and cooling, a material is born that protects millions of buildings from rain and snow, withstands 356 degrees of heat and -22 degrees of cold, serving for decades without a single crack.